Our dynamic universe. The key areas covered will be the temperature of stellar objects relating to the distribution of emitted radiation over a wide range of wavelengths, and the wavelength of this distribution is shorter for hotter objects than cooler objects. Qualitative relationships between radiation per unit surface area and temperature of a star, and cosmic microwave background radiation as evidence for the Big Bang and subsequent expansion of the universe. What we will do today is state how temperature of stellar objects is related to the wavelengths of the radiation they emit, describe how their wavelengths vary for hot and cold objects, state the relationship between radiation per unit surface area and temperature of a star, and describe the Big Bang theory, and give evidence to support the Big Bang theory. The Big Bang theory. What happens to the color of objects as they are heated? When an object is heated, it does not initially glow, but radiates large amounts of energy as infrared radiation. We can feel this if we place our hand near but not touching a hot object. As an object becomes hotter, it starts to glow a dull red, followed by a bright red, then orange, yellow, and finally white. This is why we call things white hot. At extremely high temperatures, it becomes a bright blue-white color. Practical application: pottery. Early potters used the fact that materials glow at different colors at different temperatures to determine the temperature inside of their kilns. In 1792, the famous porcelain maker Josiah Wedgwood noted that all bodies became red at the same temperature. We can see this in the table here. At dark red, the temperature is 550 degrees C, and this increases all the way up to the color of white at 1200 degrees C. Light and temperature. We can see that the temperature of an object affects the light it gives off. This means that the temperature of an object is linked to both the frequency and the wavelength of the light it emits. A graph of intensity versus wavelength has a characteristic shape and can be shown in a Planck distribution. Planck distribution, also known as a blackbody spectrum, and it has three main features. We can see a little picture at the bottom there. I'll show it bigger on the next slide. But 1, the basic shape is more or less the same. 2, as the temperature of the object increases, the peak intensity wavelength decreases, so frequency increases. 3, as the temperature of the object increases, the intensity and energy increases. This is summarized as follows. If the temperature goes up, the wavelength goes down, therefore the frequency goes up, the intensity goes up, and the energy goes up. This is a large version of the graph there. You can see that for all of the temperatures, the shape of the graph looks roughly similar. We can see that the peak wavelength decreases as our temperature is increasing, and again, as our temperature is increasing, our intensity, which is our y-axis, is also increasing. The graph shows how the energy emitted per second from the surface of a hot object varies with the wavelength of the emitted radiation at different temperatures. A student makes the following statements based on the information shown in the graph. Which of these statements are correct? We'll go through them one by one and discuss whether they are right or wrong. Number 1. As the temperature of the object increases, the total energy emitted per second decreases. Let's have a look at the temperatures. We can see 3000, 4000, 5000 and 6000 there, and it's saying the total energy emitted per second decreases. Our y-axis is saying energy emitted per second, and we can actually see this is increasing. They say it decreases, we say it's increasing, so that one is wrong. The second point, as the temperature of the object increases, the peak wavelength of the emitted radiation decreases. So let's look for our peaks. We've got one here, 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 and here. So we can say as this temperature is increasing, we can definitely see those peak wavelengths are decreasing there. So that one is correct. The third point, the frequency of the emitted radiation steadily increases as the emitted energy per second decreases. So that's saying energy decreases and frequency increases. We know that's wrong. As the energy goes up, the frequency also goes up. So this is wrong. 2 only, that's going to give us an answer of B.
Why is the sky dark at night? You might think the answer is
So what have we learned so far? Redshift. When objects move away from us, their wavelength is increased. We now know that galaxies are moving away from us. Hubble's law. This can help us work out the speed and distance of stellar objects. We now know galaxies are further away from us, are speeding up. Expanding universe. Scientific evidence shows us that the universe is expanding, and this expansion is accelerating. What does all the evidence above tell us about the beginning of the universe? So how did the universe begin? There was a sudden appearance of energy which consequently became matter and is now everything around us. There were two theories regarding its beginning. One, the steady-state universe, where the universe had always been and would always continue to be in existence. And two, the created universe, where at some time in the past the universe was created. What is the Big Bang Theory? The Big Bang took place around 13.8 billion years ago. The universe was originally very hot and very dense, concentrated in a tiny point known as a singularity. This was smaller than an atom. It caused our universe to expand suddenly from the singularity, bringing time and space into existence. Following the Big Bang, temperatures rapidly cooled and tiny particles of matter began to form. The first atoms to form were hydrogen and helium. This matter created stars, galaxies, and planets. What evidence is there for the Big Bang? There are a number of factors that provide evidence for the Big Bang. One is the expanding universe, two is cosmic microwave background radiation, and three is the abundance of light elements. 1. The expanding universe. Light from the stars in the galaxy is enough to light our sky at night. The only explanation that our sky is not completely bright at night is that the stars are moving away from us. An expanding universe must have started out infinitely small and agrees with the Big Bang theory. 2. Cosmic microwave background radiation. This radiation can be detected on Earth coming from all directions in space. This radiation is constant throughout the universe. As the universe expands, the wavelength of the radiation emitted increases, which is less frequency, down to the microwave region. This radiation provides a constant temperature throughout the universe, approximately 3 Kelvin. 3. Abundance of light elements. The universe has an abundance of light elements such as hydrogen and helium. As the universe grew, these elements fused together to create other known elements. The cooling of the universe and cosmic microwave background radiation provide evidence for the photoelectric effect, the Bohr model of the atom, the theory of special relativity, the Big Bang theory, or Newton's universal law of gravitation. We know what we've been studying recently is about the Big Bang theory. This is an obvious question there. Our answer is D. All stars emit radiation with a range of wavelengths. The peak wavelength of radiation, lambda peak, emitted from a star is related to the surface temperature, T, of the star. The table gives the surface temperatures in Kelvin of 4 different stars and the peak wavelength radiated from each star. Use all the data in the table to show that the relationship between the surface temperature T of a star and the peak wavelength radiated, lambda peak, from the star is T equals 2.9 times 10 to the negative 3 divided by lambda peak. So what we're trying to do is show this equation just here. If we rearrange this slightly, we can get T lambda peak equals 2.9 times 10 to the negative 3. This is something we can work with because in our table we are given T, temperature, and lambda peak, which is our peak wavelength. So for all rows in the table, we want to multiply our temperature and our wavelength together and see what we come out with. So I'm going to label these 1, 2, 3, and 4. So for 1, we've got 4,200 times by 6.90 times 10 to the negative 7. What we get for that is 2.898 times 10 to the negative 3. For the second one, I'm not going to write down the working for all of them, we're just going to multiply the temperature by the wavelength, and I'll write down the answers for these. So for the second one, we got 2.900 times 10 to the negative 3. For the third one, we get 2.884 times 10 to the negative 3. And for the fourth one, we get 2.904 times 10 to the negative 3. We can see from these answers that our T multiplied by lambda peak is equal to, we can take an average of them, we get approximately 2.9 times 10 to the negative 3. This is proving our relationship that we were asked to. Part B. The blue supergiant star Eta Carinae is one of the largest and most luminous stars in our galaxy. It emits radiation with a peak wavelength of 76 nanometers. Calculate the surface temperature in Kelvin of this star. So let's write down our equation. T equals 2.9 times 10 to the negative 3 over our lambda peak. And we are given our peak wavelength, so we can just add this into our equation. 2.9 times 10 to the negative 3 divided by 76 times 10 to the negative 9, because that's in nanometers. We get a final answer of 38,158, and we can write this as 38,000 Kelvin. We don't want to round it to 5 significant figures, as the question gives us a number with 2 significant figures. So we can round to a maximum of 4 significant figures there. It's easiest just to leave it as 38,000 Kelvin. Part C. Radiation of peak wavelength 1.06 millimeters can be detected on Earth coming from all directions in space. 1. What name is given to this radiation? We know this radiation is called cosmic microwave background radiation. We need to remember to say cosmic microwave and background to get all of those marks. You cannot just abbreviate it to CMBR, as this is not naming, that's just giving an abbreviation. Part 2. Give a reason why the existence of this radiation supports the Big Bang theory. There are a variety of answers we could choose for this, but we could take one of the following. It is pervasive throughout space. It's the dominant source of radiation in the universe. It is very uniform throughout the universe. It is isotropic throughout the universe. It shows the characteristics of black body radiation. It has a temperature of approximately 3 Kelvin due to the cooling on expansion. It corresponds to a redshift of 1000, so the early temperature of this radiation was approximately 3000 Kelvin. And CMBR is thought to be the afterglow of the Big Bang, cooled to a faint whisper in the microwave region. Experimental work at CERN has been described as recreating the conditions that occurred just after the Big Bang. Describe what scientists mean by the Big Bang theory and give one piece of evidence which supports this theory. During a television program, the presenter states, "Looking through a telescope at the night sky is like looking back in time." Use physics principles to comment on this statement. Let's try the first part of the question. First of all, we need to mention a description of the Big Bang theory. For example, the universe was initially hot and very dense state and then rapidly expanded. The universe started from a point/singularity and rapidly expanded. And then you need to include one supporting factor, as the question is worth 2 marks. You could include the abundance of hydrogen or helium. You could include CMB/present in temperature of the universe. You could include the darkness of the sky and redshift of galaxies or Olber's paradox. We have to use physics principles to comment on the statement, "Looking through a telescope at the night sky is like looking back in time." This is worth 3 marks, so you need to do a bit of writing for this. First, we could say light travels at approximately 3 × 10⁸ meters per second. 1 light year is the distance travelled by light in 1 year. This is 9.46 × 10⁻15 meters. As stars in our galaxy can be well over hundreds and thousands of light years away, the time it takes their light to reach us is massive. For example, our nearest star, apart from the Sun, is over 4 light years away. This means that the light we see from this star was sent over 4 years ago. Effectively, we are looking back in time. According to the lyrics of a popular comedy song, the universe itself keeps on expanding and expanding in all of the directions it can whiz. As fast as it can go, at the speed of light, 12 million miles a minute, and that's the fastest speed there is. Use your knowledge of physics to comment on these lyrics. I've linked to the song above if you want to watch it, but we're going to answer this question without doing that. First, we can comment on the universe itself keeps on expanding. Yes, the universe is expanding. We know this because of stars and galaxies moving away from us, and cosmic microwave background radiation, and the abundance of light elements. In all directions it can whiz. It is expanding in all directions with the space in between each galaxy increasing as they move away from each other. As fast as it can go at the speed of light. This lyric is wrong as it suggests a constant speed, however the expansion is actually accelerating. 12 million miles a minute. Using 1,610 meters per mile, this converts to 1.932 × 10⁻10 meters a minute, which is 3.22 × 10⁸ meters per second, and this is slightly more than the accepted value for the speed of light. The fastest speed there is. This is true as nothing can travel faster than the speed of light. Here is an open-ended question to try. Watch the video for the song Big Bang Theory by the Barenaked Ladies, which is the theme tune for the Big Bang Theory TV show. Use your knowledge of physics to comment on the accuracy of the physics in the song. You can press the triangle to go and watch it, or you can follow the link at the bottom.